In the previous video, we have introduced how the register count impacts the overall performance, and one term we introduced is the occupancy of a GPU. So occupancy basically describes the number of wavefronts that can concurrently run in each compute unit at the same time. Remember when we introduced the GPU architecture, we mentioned that each compute unit can run 40 wavefronts at the same time. So if we can only run 20 of them, the occupancy is 50%. If we can only run 10 of them, the occupancy is 25%. So why we care about occupancy? We need to tie back into the performance discussion that when we talk about thread level parallelism. When we have a lot of threads to run, one thread may be loading the memory while the other threads may do calculation. In this way, we hide the memory access latency. Memory access are slow, so we need a lot of threads to do the calculation to hide the memory access latency. In this sense, we want as many as possible threads running in one compute unit at the same time. But there are resource limitations. We have wavefront slot. Each SIMD has 10 wavefront slots. We have vector register size, we have scalar register size, and then we also have LDS size. If one wavefront is occupying a lot of vector registers or local data share memory, which we'll introduce later, then the number of wavefronts that a compute unit can run is limited. So I have to say at this point, increasing the number of wavefronts in one compute unit may be a good thing in theory, but may not be always a good thing. On one side, we can hide the memory latency, but on the other side, if we have too many threads or too many wavefronts that loads memory, they may thrash the L1 cache. They may compete for L1 cache sizes. Each of them may miss from the L1 cache, and they may have even lower performance. So sometimes we want to find the sweet point of the occupancy and not too low and not too high. So in this video, we're going to discuss the performance impact of occupancy and how to tune occupancy if the occupancy is too high. Let's look at this vector add example. It is just a vector add we have been talking about many times before. And it's not a fixed size kernel. So in theory, each thread in this vector add kernel only occupies a few registers and do not really use LDS size. So it will only occupy one wavefront slot. So the occupancy of this type of kernel can easily achieve 100%. Is it a good thing or bad thing? In general, for this type of kernel, it is a good thing. We want the occupancy to be as high as possible. But what if we want to lower the occupancy? We can actually introduce LDS size, and this is one way of allocating LDS size. So here, we allocate the LDS size to be 1 byte. We can change this number to whatever we want. And we define the type as floating point numbers, so each element will take 4 byte size. We prefix this array using __shared__ modifier to notify the compiler this is shared memory. We also add a volatile keyword. In general, you don't need a volatile keyword. We want to add this volatile keyword because we don't want the compiler to optimize it out. And at the end, we add if a_tid equals 0, because in this case, I know it will never equal to 0. I add some dummy code there just to prevent the compiler from optimizing that out. This if statement will never get executed. So we have one knob. We have the LDS size as a knob. We can change the LDS size to tune the occupancy. If we use a super high LDS size, we may not be able to run a single wavefront in each compute unit and the execution will fail. But if the LDS size in each compute unit can only handle one wavefront, then we have an occupancy of 1/40. Now, as we change the LDS size from 0 to a very large number, we can tune the occupancy to be 1 to almost 0. So let's see the performance. And this experiment is done on an M100 GPU. We want to change the LDS size in bytes to check the performance. As we can see here, we can clearly see this execution time has stairs. When we have an LDS size that is greater than 32K, our occupancy is 1. That means there's only one wavefront that is executing in one compute unit. And the execution time is high. As we reduce the LDS size, we see the stair goes down to almost half of the value, from 6 microseconds to 3 microseconds. So the performance almost doubled when the occupancy turns from 1 to 2. As we keep reducing the LDS size, we can see the occupancy become 3, then our performance keeps improving. As we keep reducing the LDS size, our occupancy becomes 4 or even greater than 4. After 4, I cannot clearly see the stair boundaries, and when the occupancy turns from 4 to 5 to 6, it's hard to tell where it happens. But as you can see, the fewer LDS size that I use, the higher performance we will see in this example. So this example is not to tell you that the higher occupancy the better, but in general, the higher occupancy the better. To achieve the sweet point, you may want to use the LDS size to tune the occupancy to the desired value by doing experiments.